So, it is time for our mystery speaker and mystery talk. Would the mystery speaker please come and give their mystery talk? It is Aki.
Is this on? Yeah.
All right, we got you hooked up.
Good afternoon. I'm honored to be the guy who's asked in to make fill in the empty slot with the less than 24-hour notice. I hope my talk is not complete mystery. Okay. So I used the opportunity to talk about regularized horseshoe. And this is joint work with Juho Piironen. Okay. So outline of the talk is this horseshoe prior, regularized horseshoe. It's useful in large P, small n regression when we have a lot of covariates, but not many observations. Talk a little bit about priors on weights, and on the other hand, how we can think about then on priors on shrinkage, horseshoe prior, and then regularized horseshoe prior. So mostly the large P small n regression has been linear or generalized linear regression. Of course, we can also go to nonlinear models, but now I talk just about these linear, generalized linear cases. And these are common like in modern medical bioinformatics studies, microarrays, genome-wide association studies, brain imaging. In our examples, the number of covariates is usually from 100 to 10,000, and most of the experiments we've run have been observations less than 100. If we have noiseless observations, we can fit uniquely identified regression in n-1 dimensions. Otherwise, we can just fit a hyperplane which goes through all the points. If we have noisy observations, this is a bit more complicated, but in a way you can think about this starting point, what we can learn from the data. If we have correlating covariates, it is also more complicated that how many observations can be fitted completely. So it's clear that we need priors because data alone can't then identify this regression model. There's then two cases, the non-sparse priors, which assume that most covariates are relevant, but there's strong correlations. And these are factor-type models, and I'm not talking about them today. And sparse priors, which assume that only small number of covariates are effectively non-zero. We still might have also correlations between this smaller set of covariates, but it's, the important point is now that we assume that only small number is relevant anyway. Quick visualization, what this kind of sparsifying prior can do. This is just the toy data with a Gaussian prior, and plotted these marginal posterior distributions there, and then horseshoe prior, and we can see that most of those marginals have been shrunk a lot towards 0, and then it's more easy to see which of the covariates are relevant. And also, in this case, adding this prior, because it happens to match now the truth, it also improves the predictive performance. Here's the comparison with using the loop package. I'll talk more about loop package tomorrow in model selection tutorial. There are different kind of sparse priors. There's many more than I will mention today. Most common ones are the Laplace prior and spike and slap prior. And now then the horseshoe is more recent one, which is gaining popularity. The Laplace prior has been popular because of computational convenience, continuous log concave, but it's not really sparse. You can see some results later. Spike and slap with point mass at 0. Then the problem is that we have a discrete parameter space, and we can't do that in Stan. And also, the discreteness makes it difficult for MC to know where to go next. And then with horseshoe and regularized horseshoe, we have a continuous prior. We get good similar properties and spike and slap, but also MC is easier with the continuous model and gradients. So here you can see, so the lightning is not the best possible. There are different shapes. All of these priors have more mass near 0, and then some tail. Looking at these kind of figures, it's not so easy to realize what is the actual effect on these. So let's look at how they look at for shrinkage. The amount of shrinkage for specific value, parameter value, depends on the how steep that distribution is that point. So we can also see it here then that the horseshoe is very steep here, so it's not shrinking much. And then if we would look at the tails more carefully, we would see that on the other hand, horseshoe also gets really flat on the tail, and so it's not regularizing there much. So here in these figures, the kappa is now the amount of shrinkage, going from 0 to 1, and we can look at then how these different distributions, how much prior mass they put on different shrinkage values. And we can see that the Laplace prior is not that good because it doesn't put much mass on that there would be no shrinkage at all, so it's shrinking all the time, also the relevant ones. The horseshoe gets the name from this, that with the specific parameter values, it looks this U-shape, the horseshoe shape. And now we have the property that it gets more mass that there's many coefficients which should not need to be shrunk at all. So those are our relevant covariates. And on the other hand, then there's a lot of mass here saying that these should be shrunk completely. We can also plot the same thing for spike and slap prior, the same shrinkage figure, and for the spike and slap, we get just point mass on 0 and point mass at 1. We can now also then vary the parameters of the horseshoe or spike and slap. We can vary how much mass we put on the no shrinkage and a lot of shrinkage case. The horseshoe prior, it's a hierarchical prior, so we have here betas, conditional, they have a normal distribution, we have a local term, global term, and if we choose for the local term half Gaussian prior, for the local terms, we choose the half Gaussian prior, we get the horseshoe prior. And then by varying this tau, the global term, we can then vary, we go here, look at the picture, we can vary then the shape and how much mass we put there. Now it's nice that we can look at this amount of shrinkage, but then it's even easier to interpret this if we go look at the effective number of non-zero coefficients, so effective complexity of the model. So here we have again the kappas. So the kappas were the shrinkage factors from 0 to 1. And then if shrinkage is 0, we have effectively 1 parameter. So in the summing term, we get the 1. And if the kappa, the shrinkage is 1, then we get effectively 0 from the term. And then we sum over all shrinkage coefficients for each covariate coefficient. And then we get effective number of non-zero coefficients on our model. And it's easier then to think about priors for that. And then there's happens to be a nice connection so that it's easy then if we have a prior guess for MF, how we can compute tau. You can look at the details in the papers. I'll just show figures. Toy example, n observations 100, and our prior guess is that there should be 5 non-zero coefficients, and then we can put in this information. And now there are different plots so that here we've just fixed the tau 0 based on these equations from our prior guess 5. You can see now that then our prior is around the 5. This is a case where we assume there's a total of 10 covariates. This is a case where we assume there's a total of 1,000 covariates. And again, the prior is around 5, about from 1 to 10. We can make it more flexible. So if we don't trust our prior guess on how many non-zero coefficients there would be, we can, instead of fixing the global scale, we can have a prior, half normal, or half Gaussian, and we can see that then we still have it around the 5, but the tail gets longer. And then the last one is just showing that in the original Horseshoe paper, they were proposing something which didn't take into account anything about the we would like to have it sparse, and the original Horseshoe paper prior is actually quite awful, saying that most of the mass is with all coefficients being relevant. And so this reference value, so there was this equation for tau 0, so the global scale, and you can see it includes now the prior case, the P0, the dimensions, the total number of parameters. It includes also sigma, and this will make it also to scale then based on the accuracy of the observations. And in case of non-Gaussian observation models, we can then use Gaussian approximation to the likelihood and use plug-in values to make it work also there. Now the problem with the horseshoe is that it allows some coefficients to be completely unregularized. And this is a problem then that it allows complete separation in logistic models. When we have n smaller than p, it's likely that we can find again a hyperplane dividing all observations belong to one class and to the other class. And that's the problem because we have now the prior is saying that the zero shrinkage is possible. Now the regularized horseshoe fixes this one, adding additional prior, which has an effect for when we're looking at the prior on the shrinkage scale, that we can move the horseshoe where it is slightly away from zero. This is the same we can do also for the spike and slab. That can't be true. And we can see that here, example case where we used horseshoe. Look at these beta 1 and beta 2 values in logistic regression. So there's a beta 2 going up to 100,000. And with the regularized horseshoe, depending on parameterization, we get betas less than 10 or less than 30. And that helps a lot. This is easy in RStanArm, thanks to Ben Goodrich. It's actually using by default these values, except it has some default for tau 0, but you should set it. It doesn't allow the conditioning on sigma, so for that you need to write your own Stan model. Luckily the result is not sensitive to the exact value, so you can just use plugin value there. And note also that when you look at the RStanArm manual helps, it's called the hierarchical shrinkage prior because it includes also other versions than horseshoe. Simulated regression example, N100, P200, true is 7. Let's look at the with the Gaussian prior. Oops, we don't find 7 non-zero ones. Everything's slapping 0. Bayesian lasso. Yeah, it's narrower in the middle, but nope. And the horseshoe. And here are the 7 relevant ones. And we can also compare the true values in the simulated example, and they fit nicely in the line. These are kind of the bigger data sets we've experimented. There are also some experiments up to almost 20,000 dimensions, slightly larger ends also. And just showing that if you go to a paper, you can find these figures which show that it beats lasso, GLMNet package, and the regularized horseshoe also get rid of divergences in Stan. And tomorrow I will talk about more in the model selection part that even if you use a horseshoe, after using horseshoe, you can then more easily choose the relevant variables. And to end, it is producing like the prior as sparse as horseshoe, but it's more robust inference, more robust computation, and we get better performance than lasso and Bayesian lasso. And there's the references, and there's the example code for Stan models in the articles, and then the RStanArm at this.
All right, I'll ask the first question. I know, so I'm feeling a little sad. We're almost done with the second day, and it's going to be, StanCon's going to be over Friday. And I'm just wondering, it's like, gosh, could we have a StanCon that's not in California again, and certainly not New York City, because, August is, or whatever we'd have it in, It's just a terrible time. You have any input on this, Aki, that you could possibly help us, my existential angst in not having any StanCon time?
Yeah, here's my answer. Anti-etic sampling. So this is a term for cases when Markov chains with lag 1 have an autocorrelation, negative autocorrelation. This is actually possible. We've seen also this with the nuts. It's just that currently the NF computation has a small feature we are fixing so that soon you can see NFs larger than N with Stan. But a simpler example than the nuts. So the first StanCon was in New York. Now we are in California. And so what would be the negatively correlated location from California? So when I left from New York coming here, the travel time here was about the same as for the next place. And I should have it here. And how the next sample looks like, it's here. It's going to be warmer. And the website is also here. So, and notice it's already in August, so it's also 2018. We are too eager to have this kind of conference again. And also, this is going to be then the first StanCon in Europe. So we are certain that we are going to get also then a lot of European Stan people to join.
All right. Anyway, Aki is around to ask the technical, if you want to ask him technical questions, he'll be around consulting and stuff. Thank you very much. That was really nice. What?
If someone has something about horseshoe?
Do you want to, what time is it?
35.
25? All right, we have 5 minutes. All right, horseshoe questions. Quickly, okay, here.
Hi, thanks. I'm using prediction accuracy for lasso models to estimate how much genetics play a role for various traits. And I would love to use something like this instead. But I might have 10,000 observations and 5 million or up to 30 million variables. Is that feasible at all in Stan or in anything?
Only if you do some dimensional reduction first.
Okay, so what would be the upper limit of like the size of the problem?
I'm not sure then. So the largest we've experimented with have been tens of thousands features and thousands of observations. To do this kind of the and even that when we do it in two stages, so the dimensional reduction first and then the Stan and horseshoe, even then the computation time is already quite a lot compared to many more like ad hoc approximations, and then it's a work in progress in a way that how much better performance we will get with doing it as Bayesian as possible. We know that in some cases, yes, and of course one thing is that with Stan, it's easy to use different likelihoods. So it seems that now if you are just having a logistic regression or just a Gaussian regression, you might get useful results also with other approaches. And one thing is also that when we started doing these kind of things, we had also collaboration with people doing these genome-wide association analyses. And in the beginning, they didn't have so many observations, and they were interested in this.
Yeah.
And a couple of years, and then they had hundreds of thousands of observations.
Yeah, it's getting bigger, yeah.
And in the same way, if you can get more observations, It might be easier, but I'm interested in talking more if you have a problem that you can't get more observations.
Awesome. Let's thank the speaker.